Welcome back to this second video here in 12.1, vector valued functions. In this video, we are going to create our own vector valued functions. And we're going to start with one that we've essentially already done. I want to find a vector valued function to represent a line segment, which is basically a line. A line is just the whole thing. A line segment just says, hey, only use some of the t values. But that means we already know really what to do. That basically means that we're going to start by finding the line from P to Q. And there's going to be more than one answer to this. There's one pretty straightforward answer that's very common. Now, how do you find a line? Remember this, you need a point on the line. We got multiple options. I'm going to go with P, 1, 3, negative 2. I'll show you what changes briefly when you make a different choice in a moment. We need a direction. I'm going to use the direction PQ, which is 1, negative 4, 5. And then I'm going to write down the equation of the line. I'm just going to do it as a vector here. The line basically is the point P plus T PQ, the direction. But what does that actually look like for us? I'm going to write it as a vector, 1, 3, negative 2, plus T times 1, negative 4, 5. And when we put it all together, it's 1 plus T, it's 3 minus 4T, it's negative 2 plus 5T, and there we go. A vector valued function, and here's what else is true. When you plug in T equals 0, you get out P. You can see that very clearly actually here. When you plug in T equals 0, you don't get the PQ, you just get P. You get 1, 3, 2. When you plug in T equals 1, well, if you look at this formulation of it, you start at P and you add 1 PQ. Now, PQ is the vector that moves you from P to Q. You end up at Q. You can also work that out algebraically. You can plug in T equals 1. You'll discover you're at Q. And so what that means is that if I just want the line segment, that I've got the whole line. I've got P, I've got Q, and I've got the whole line connecting them. But what we just discovered is P is T equals 0, Q is T equals 1. And so all I have to do is just say, hey, I'm just going to use 0 less than or equal to T is less than or equal to 1. And that gives me this chunk nicely right in between there. Starting at T equals 0, going to T equals 1, we got the line segment. So it's basically writing down a line, and if you use your starting point as your point on the line, and you use your direction vector as the entire line segment, you're just going T equals 0 to 1. Now, if you're trying to show off, you could use Q as the point. And that means T equals 0 is Q, and if you still use PQ, then you've got negative 1 here. That's fine. There are other ways that the line can be written down in lots of ways. You just need to figure out, hey, what time gives you P, what time gives you Q. And because we want to go from P to Q, you would better have this orientation. If you don't have that orientation, you're going to need to sort of flip things around. The easiest way to do that is to just turn your direction vector around, because then you're going the other way. So multiple answers here, but this is sort of the straightforward one. As we get forward into the class, especially when we get into chapter 15, we will very, very much need to be able to write down these. We'll need it in chapter 13 as well. We'll definitely want to be able to write down line segments that travel from one point to another. And this is the easiest way to do it. It's basically writing down a line. Here's a more complicated vector valued function that we're going to write down, though. I've got two surfaces. I've got a semi-ellipsoid. It means it's an ellipsoid. It's an ellipsoid because, hey, we got x squared positive, y squared, z squared, all positive equals 1. It is an ellipsoid. The semi part just says, hey, we're looking at half of it. We're looking at the top half of this surface. So let me draw this shape. Basically a sphere, except for it's squashed in some dimensions. So there's my semi-ellipsoid. Let me, now that I actually have that in there, draw my x-axis, my y-axis, my z-axis, piercing right through the top center of it. There's my semi-ellipsoid. more or less. I also have a parabolic cylinder. What does that mean? Well, a parabolic cylinder, this means that this is one of the mathematician cylinders. This is y equals x squared, which is just a regular parabola. Now, it's a regular parabola in the xy plane. So let me actually draw that. In the xy plane, it's going to look like this. So just flat on the ground there. And then because it is a parabolic cylinder, it's going to just go up, basically. And it's just going to be that same shape all the way through. And so you end up with sort of this kind of thing running through space. Now, where is that going to intersect? Well, it's this sort of straight vertical thing, but as it comes in and intersects this curve, we got an intersection down here at the bottom, we got an intersection there. It's going to sort of be this kind of intersection, and it's going to be sort of like this kind of intersection going across the surface. I do want to show this to you. So here we are. I've got my ellipsoid. You can see it actually more accurately now. I've got my parabolic cylinder, this sort of vertical parabola. If you actually rotate this way, you can see it's just a regular parabola, y equals x squared, but then just lifted up. And we've got this intersection that I've got highlighted here, and it sort of comes from this top point where they both are, and it sort of slides down the ellipse until we hit that parabola. And so you'll notice what's true about that intersection is that every point of that intersection is on the parabola. Every point on that intersection is on the ellipsoid. And so both things have to be true. How are we possibly going to find that curve? Now, if you've got really, really good eyes, you can see what it looks like over here, but that's not a useful thing. How are we going to work out what this actually looks like? Well, the answer is to do something like this. The answer is to just sort of start guessing here. And so here's a thing to try. And we're going to try not the whole thing. We're going to just try x equals t. And we're going to start with that because in the parabolic cylinder, it's really that kind of thing. We're going to try x equals t. So here's what my tentative function looks like so far. Blank, blank. But x equals t, this is called sort of inserting a parameter or parameterizing the function. Often just trying by starting with an x equals t or a y equals t or a z equals t is going to be helpful. We're starting with x equals t. What can I deduce from that? Well, then y equals x squared. But we get to go in and say, we now know what x is. X is t. So y is actually just t squared, and we figured out the y function. What the y function has to be. Basically, we're saying, hey, if you chose x to be t, y's always got to be x squared, because we are going to be talking about stuff on the parabolic cylinder. But what about z? Well, here's what we know. We also have our semi-ellipsoid, and you could solve your semi-ellipsoid for z right off the bat, or you could say, hey, our semi-ellipsoid is now t squared over 12 plus t squared squared over 24 plus z squared over 4 equals 1. What have I done? I've just said, hey, here's x and here's y, but we figured out what those functions are. We know that x is t, so I'm basically going to take every x you see on this entire slide and replace it with t. We know that y is t squared. I'm going to take every y that you see on this slide, most notably the one in our semi-ellipsoid, and replace it with t squared, and then I'll solve for z. When I solve for z, we get a lovely function here. The first thing I'm going to do is I'm going to take the whole equation and I'm going to just multiply it by 24 on both sides. That gets me 2t squared plus t to the 4 plus 6z squared equals 24. I'm doing that because fractions are not fun. I'm going to subtract a bunch of stuff. 6z squared equals 24 minus 2t squared minus t to the 4. And then finally, I'll divide by 6. z squared equals 24 minus 2t squared minus t to the 4 over 6. And then take a square root to find z. Now when you take a square root, it's plus or minus, but we got one extra little bit. Z is bigger than 0. Positive square root 24 minus 2t squared minus t to the 4 over c. Now you can also sort of work out what the domain of this thing has to be. In particular, the easiest way to do it is to just figure out what the biggest z coordinate is going to be here and try to work from that. You can also work from the x and the y coordinates, but you can sort of work your way through that. But literally what I did in GeoGebra when I wanted to type this whole thing in is I said, hey, I'm just going to type literally exactly what we just got there. So let me bump up the font size just a bit. And I didn't even come particularly close to getting the domain. I just went big enough. But I said, hey, x equals t. That was our guess. Y equals t squared. That was our next deduction. And then calculate z. Now, before we go on, I do want to say, hey, what would have happened if we had tried something else? What would have happened if I had tried y equals t? Well, let's just see what happens there and see if we can sort of work out whether that's going to be okay. If instead you tried y equals t, then t equals x squared, so x equals plus or minus root t. That's not great. And so that would be an indication that maybe we should be a little bit more careful with this, because we don't like having multiple values there. So that might be an indication that we should try going back and trying a different parameterization. But sometimes the one that we can come up with is really in two pieces. So you might say, hey, I'm going to actually just run two parameterizations, one where x is positive root t, one where x is negative root t. And then you'd plug it in here and maybe you get something that is nicer in that case. You would definitely get another parameterization. The default would just be if you only used x as positive root t. You'd only get the positive x values. You'd only get the front half towards us of this shape. Trying z is going to be much harder, because z doesn't actually show up in both of them. So you really want to start with x and y here. So that's how we find these parameterizations. Let's do another one. I want to find a vector function that represents the curve of intersection. We got a cylinder. This is, your standard actual cylinder, and a plane. So let me, first of all, try to draw this cylinder. Let me draw my coordinate system with an x-axis, with a y-axis, and a z-axis going up. I'm going to try to draw this plane. Now this plane, I'm going to find this sort of various where it intersects the coordinate system. Y plus z equals 2. When y and z are 0, it doesn't work, right? That this is actually another cylinder. It's just going to be straight in the x direction, cutting through in a sense here. But when x and y are 0, you get z equals 2. And when x and z are 0, you get y equals 2. So I get sort of this cut through and then coming straight down the x-axis. So that's our plane. Now where's it going to intersect? Well, it's going to intersect this cylinder somewhere out here, and then it's going to sort of come around to this, and it's going to go around back here, and the plane keeps going. And so we end up with this sort of taking this can and just slicing up at a diagonal angle through it, and we're going to get a shape. This shape is going to be very circular. It's going to be very elliptical, actually, is technically what it is. But because it's circular, here's what we know. We got x squared plus y squared equals 1. Now, you could do a bunch of different things here to try to work this out. One option would be to say, hey, let's just try, because y appears in both of them, let's just do y equals t to parameterize this. So we'll write down this answer. We'll have a blank, we'll have a t, we'll have a blank. Now, from the second equation, y plus z equals 2, so z equals 2 minus y, so z is 2 minus t, 2 minus t. Beautiful. How about x? Well, we know that x squared plus y squared equals 1. That's x squared plus t squared equals 1. X squared equals 1 minus t squared. That's x equals plus or minus square root of 1 minus t squared. Okay, so if I just put the positive, because it needs to be a function, plus or minus makes something not a function. If I just do the positive, what that does is it means that the x is positive, and I'm actually only tracing out just this front half of it, where x is positive. How do you get the back half? You do a negative sign. Okay, so you've traced out the curve. Technically, we haven't answered the question. Find a singular vector function. We found two of them. Now you could sort of glue them together in some sort of weird way. But really, what's going on here is that the x squared plus y squared equals 1. If you choose x, then you're going to solve for y, and it's going to be a plus or minus square root. If you choose y, you're going to get a plus or minus square root for x. Those aren't going to really create a function until you recognize this. X squared plus y squared equals 1 is a circle. And so use circular functions. X equals cosine t. Y equals sine t. That's how you describe circular motion, circular behavior. Anytime there's a circle, and we've got a circular cylinder, there's a circle, x equals cosine t, y equals sine t, and then z is 2 minus y is 2 minus sine t. And so if you actually set this up as cosine t, sine t, 2 minus sine t, then you will get the entire curve, and you can actually, because it circles around, you can just go 0 is less than or equal to t, less than or equal to 2 pi, and you get this intersection. Let's check out a picture. Here we are. I've got the cylinder. I've got the plane just slicing through. This plane has nothing to do with the x-coordinate, so it is just in the x direction. And you can see visually the intersection there, that it is, well, you lose the circle, but you get this sort of elliptical intersection. And if I do that first parameterization, where I just take the positive square root, you see that we actually only get 1/2. You only get x is positive. It looks like negative, but that's because the x-axis is going left right now. You only get 1/2 of it. If you want the whole thing and there's a circle involved, and there very much is a circle, then you got to use a sine and a cosine, or circles or ellipses, things like that. Sines and cosines are the tool. Anytime you think there's something circular going on, see if you can come up with a parameterization using those. X equals cosine t, y equals sine t. Use coefficients to basically cancel out any elliptical stuff that's going on. Often a really, really good idea to be thinking about if you believe that your whole piece is going to be a circle all the way through. And so that's the way to really get this parameterization down. We'll be doing a bunch of these. It's really sort of a puzzle, a problem-solving kind of thing. You want to try to meld the idea of geometry and algebra here. You want to be trying to get at least some sense of what type of shape it might look like as you work your way through. And then you want to take these ideas of, hey, maybe we try it just x equals t or y equals t. Maybe we have to use circular stuff. Maybe we have to get more creative and look for some pattern and some other way to describe things. We'll see some more of those as we go through. But for now, that's it for this video. In the next one, we'll keep going with vector valued functions. And we're going to talk about limits and continuity and some other calculus-y type things. So get ready for it.